Hello everyone. Today we are going to start with numerical double integration concept. What's the basic idea? Okay, so if you are given some integral function like this, integration a to b, c to d, f of xy, dx, dy, right? For this function, we have to integrate it by two directions. Okay, the first direction is in x direction, like for this interval. If you are having this intervals like a to b, and for this interval c to d, suppose this is the situation, what you can do here is first of all focus here on this rectangular part, right? So this rectangular part is nothing but your region given in this integral part. So over this region, what will be your behavior of f of xy? Okay, that we are going to do. So basically what we will do here is along x direction, we will integrate with respect to x. So in simple language, if you want to do like this, then a to b your f of xy dx, right? Okay, what about y here? Y is basically fixed quantity here. Okay, for example here, if you see y is equal to c. For some other layer, if you see y is equal to some other number, for example c1. In the same way, if you go here in layer wise, you will see different planes. So basically for y is equal to c, you will have one aspect or one integral. For some other y value, you will have another integral, and so on. So if you just go on in this way, you will have full region covered, right? So basically y is fixed and you just vary x from this point to this point, and hence you will have the integral a to b f of x at a particular layer y is equal to, for example, c. In the same way, you want to work with integral c to d, okay, and that's nothing but a y direction. So in y direction, we will do like this: c to d f x y dy. But here x is some fixed quantity. So here if you see c to d, the first point is x is equal to a, which is fixed. So x is equal to a will lead to this kind of structure. In the same way, if you go with some other x value, you will have another plate or another layer. In the same way, for different x values, you will have different layers. So basically in this way you will cover all these y integrals with respect to y variable, right? So overall what you can see here is basically we will try to integrate with respect to both the variables x and y, and we will develop all these basic rules that we studied earlier. For example, trapezoidal rule. So trapezoidal rule for x direction, and then you can also apply it for y direction. Fine. So in this way we can develop a trapezoidal rule for these both the directions. Okay. So now let's see one by one that how we can go with developing the first one, that is trapezoidal rule. Okay, I am just writing in short here. Trapezoidal rule for obviously double integral. So I am writing here. Yeah. So let me write here that how we will develop a trapezoidal rule in the case of double integrals. So we will write here step by step wise. Step number 1. Step number 1. Divide this interval AB into n equal subintervals, each of length h. Divide interval AB into n subintervals of length h. Right? Step number 2. Divide CD interval CD into m number of subintervals of length k. Fine. So here we have divided these whole rectangular region into hk parts, I mean m and n parts and subintervals with h and k sublength. Okay. So these are step number 1 and 2. Let's move further. So for step number 3, what we will do? We will use step number 1 and 2 in this way. We will write here xi is equal to x naught plus ih, and where x naught is equal to a, x naught is equal to a, and xn is equal to x naught plus nh, that is b. In the same way, yj is equal to y naught plus jk. You can see here this is the interval length. So y naught is c and ym is y naught plus mk, and that is d. Fine. So up to this, let's understand and make it clear. Okay. So let's quickly revise this thing. We are given two intervals a to b and c to d. We are making subintervals, n number of subintervals for interval ab having length h, and we are making m number of subintervals with length k. So xi has some notation and yj has some also notational convention. So x naught plus ih and y naught plus jk, where you can see here these are standard values, right? So now let's see that how we can go further. So in step 4, we will use trapezoidal rule for both the variables x and y simultaneously. So the output of the trapezoidal formula for double integrals can be written like this. Let's understand this now. I is equal to integration a to b integration c to d fxy dx dy. This is what we are given. Now once you apply this trapezoidal formula, then what you will get? For example, focus on this. If you have applied your trapezoidal formula for interval a to b, then it will be looking like this one, h by 2. This integral will be as it is, c to d, but change will be reflected in xi's. So here f x naught y plus f xn y plus twice f of x1y, f of x2y up to f of xn minus 1y, summation of all these x1 to xn minus 1 entities. Okay, you can just recall that this is a basic trapezoidal rule with y fixed. Okay, Now once y varies, you can see that now you come onto this second integral, that is c to d. Okay, and that is what I have written here in the next step. Just focus here, observe well. H by 2 was there and another section was k by 2. So product will be hk by 4 into bracket. Now see, basically f naught naught is same as f of x naught y naught. Okay, so I'm just writing in easy form. So f00 plus f0m. Okay, similarly f twice f01 plus f02 up to f0m minus 1. So this is nothing but you can say like the first term y naught in the original trapezoidal rule. What we were writing, y naught plus yn plus 2 times y1 plus y2 up to yn minus 1. So just we recall that original trapezoidal formula, and in analogy with that you can just see here that instead of y naught, now we have these whole terms, the full number of terms in expressed in terms of trapezoidal rule again. So f of 00 plus f0m plus 2 times f01 plus f02 up to f0m minus 1. You can see here 1, then 2, then m minus 1. These m minus 1 number of terms are there, and the first term, that is f naught, and the last term is fm. So basically you are running from 0 to m, and you are considering all the remaining terms twice. Fine. Similarly, for the nth term, that is fn0, fnm plus twice fn1 plus fn2 up to fnm minus 1. Fine. So this was about y naught. This was about yn. Like this one, you just focus here that this is the terms which are related to y naught. So it will be easier for you to remember this format. Okay, and plus twice sigma I is equal to 1 to n minus 1 into bracket f I naught plus f I m plus twice f I1 plus f I2 up to f I m minus 1. Here you note that f I j is nothing but f I comma j, or you can write f of x I y j. Fine. Now let's understand through one problem. So using trapezoidal rule, evaluate I is equal to integration 1 to 2 dx dy upon x plus y, taking 4 subintervals. Just write down here what is the information that you are given. The first one is you are given fxy is equal to 1 upon x plus y. Here a is equal to 1, b is equal to 2. We are asked to go with 4 subintervals. It means h is equal to b minus a by n. That means 2 minus 1 by 4. So 0.25. Similarly, c is equal to 1 and d is equal to 1. Instead of this 1 to 2, you may be given some other integral values as well. But fortunately here you are given a square instead of rectangle. So c is equal to 1, d is equal to 2. Again 4 subintervals means k is equal to 2 minus 1 by 4, 0.25. So now you will have a square grid 4 cross 4. Total 16 nodes are there. And if you have found any difficulty in order to understand this formula, then it will be easy on the basis of this example. So we have to consider 4 cross 4 nodes, and these are the values. F1 comma 1, you can see here, keep one fixed. Okay, so you will have another entry 1, then 1.25, the increment of 0.25 here, that is the step size h. So f1 then 1.25, f1 then 1.5, again increment of 0.25 here, it will lead to 1.5, and then f1 comma 2. Fine. The next one is f 1.25 comma 1, f 1.25, 1.25, 1.25, then 1.5. Again 1.25 is fixed, see, throughout these all. So f 1.25 and then f2. The third one is f 1.5, then 1, 1.25, 1.5, 1.2. Actually it's a mistake here to write here 1.25. Then f21, f2 1.25, f2 1.5, and f22. So these 16 entries you need to find out explicitly, and then we will use these entries in solving this problem using double integrals for trapezoidal. Okay, so what will be the structure of our formula? First of all, 1 by 4 into bracket 1 by 4 into 1 by 4. So total 1 by 64. Let me just show you here. Hk by 4. So h is 1 by 4, k is 1 by 4, and 1 by 4 is already there. So total you will have 1 by 64 that I have written here into bracket. Now see, f11 plus f12. Okay, so the extreme entries f11, then f12. Okay, what about in between entries? That will be twice f. Now see, 1 will be fixed here. So 1 will be fixed, then 1.25, again increment 1.5, again increment, and you will have 1.75. Fine. So this is our first integral. The last integral will be f of 2 comma 1 plus f of 2 comma 2 plus twice f 2 comma 1.25, 2 comma 1.5, 2 comma 1.75. Just see here. Here we had 1, then 2, and then remaining all the entries in between, which will be twice of the total summation of all these remaining entries. Similarly here, f2 comma 1 plus f2 comma 2. See here, 1 1 1 2, then 2 1 2 2 plus twice f. Now instead of this 1 you will have 2. So this is your first integral, this is your last integral. So 2, then 1.25, 2, then 1.5, increment of 0.25 here, plus 2, then 1.75. And these all three entries will be twice. Fine. So this is what we have finished for our first integral. This is for our last integral. And remaining all the integrals, you have to make it twice entry. Okay. So 2 times. Now in between, what we will have, just see here, and it will be very much easy for you. We have considered the extreme points 1 1 2 2 1 2 2. Okay, so what about the next one? That will be 1.25 obviously. So 1.25, then 1 1.25 2, again this 1 and 2, these are first term and the last terms. So remaining all the entries will be twice. So 2 times, again 1.25 is fixed. This instead of this 1 you will have 1.25. Now again take increment, so you will have f 1.25 comma 1.5 plus f 1.25 comma 1.75. It will be the increment of here 1.5 plus 0.25, that will be 1.75. In the same way, now instead of this 1.25, what will be the new entry? That will be f 1.5 comma 1 plus f 1.5 comma 2. Fine. So this is again first term, the last term, twice f 1.5 1.25, 1.5 again fixed, add 0.25 here, so you will have f 1.5 plus f 1.5 and 1.75. And the last f 1.75, because we have considered 1.25, then 1.5, and now 1.75. So 1.75 comma 1 plus f 1.75 comma 2 plus twice f 1.75 comma 1.25 plus again 1.75 fixed comma 1.5, addition of 0.25 here, and the last entry f 1.75 1.75. Complete the this bracket and the whole bracket, this one, this curly bracket. So these all entries will be twice, and these are remaining entries for those integrals. So first integral, last integral 1 1 1 2 plus twice this one, the last integral 2 1 2 2 plus twice of these three entries, and remaining all the integrals will be twice. Fine. And that's the reason that we were required to find these all entries. Okay. And hence, and how do we find these entries? It's very simple. You are given here fxy is equal to 1 upon x plus y. So for example, if you are interested to find out, say, f 1.25 comma 1, so what we will get here? We will write here f at x is equal to 1.25 and y is equal to 1. So it will be 1 upon 1.25 plus 1, so 1 upon 2.25, and that is the answer for this entry. Likewise, you can find all these entries and substitute in this formula, and finally you can check that the answer will be I is equal to 0.3407. So in this way we can find the solution of double integral problem on the basis of trapezoidal rule. Now it may be anything here. Fortunately we are given a squared region, but instead of this you might be given like 2 to 6 for example. then you can settle these subinterval length in such a way that you will have the equality, so that you can have the normal equal parts and you will have a square grid in order to understand it or work it out carefully. Okay, so this was the section for trapezoidal rule. In the same way, we can even find the formula for Simpson's double integration. So for the sake of consideration, we will have the same kind of integral. I is equal to integration a to b c to d fxy dx dy. In this case, we divide the interval a to b into 2n equal subintervals. Already we are aware about this thing, that while working with Simpson's formula, the subinterval length should be in even number. Total even number of subintervals should be there. So here we have considered 2n subintervals, each of length h. And similarly, the other interval c to d is broken up into 2m equal subintervals, each of length k. Fine. So we will apply Simpson's rule here in both the directions. Basically, the expressions are very long, so I am just focusing here in one for one subinterval j minus 1 to j plus 1 and I minus 1 to I plus 1. Okay, so integration y suffix j minus 1 to y suffix j plus 1, integration x suffix I minus 1 to integration x suffix I plus 1 fxy dx dy. So this is just for one subinterval, I minus 1 to I plus 1 and j minus 1 to j plus 1, which is equal to h by 3. If you recall Simpson's 1/3 formula, it is same as h by 3 integration, that limit lower limit to upper limit, like this one. So basically we have now employed Simpson's rule for the inner integral xi minus 1 to xi plus 1. So I kept here the first integral as it is, yj minus 1 to yj plus 1, and in bracket I have employed this Simpson's rule that will be turn out in this way: f of xi minus 1 comma y, the first section xi minus 1, here y will be as it is, plus 4 times f of xi y plus f of xi plus 1 y. And if you recall, Simpson's 1/3 formula is looking like the same one, the first term plus the last term plus 4 times the remaining terms. And here we have only three parts, xi minus 1, xi and xi plus 1, and hence you can see here that we have employed easily the Simpson's 1/3 rule. Fine. Okay, for the next stage, what we are going to do here, we are going to employ now Simpson's 1/3 rule for this remaining integral yj minus 1 to yj plus 1. So final formula will be hk by 9 into bracket. Now see, f of xi minus 1, it is same as I minus 1, and then yj minus 1. Fine. So yj minus 1. Now just be careful that we are focusing on the first term itself. First term will give you three terms. So fi minus 1, j minus 1, then 4 times fi minus 1 j, the middle one, and then again fi minus 1, then j plus 1. See, j minus 1, j plus 1. Here I minus 1, I plus 1. Here j minus 1, 4 times j, and again j plus 1. This term, these three terms, thus they are devoted for f of xi minus 1 y only, plus 4 times. Okay, so plus 4 times. Now f of xi y, for that functional format, what we are going to write here, fi j minus 1, fine, fi, that is fxi, j minus 1, j minus 1, plus 4 times fi comma j, okay, the middle one, that is now the j1, and then again fi j plus 1. So instead of I minus 1, now simply we are putting I. 4 is already there present, and this 4 is for the middle term. Okay, and similarly for the third portion, fi plus 1, I plus 1 is as it is, j minus 1, then 4 times fi plus 1 comma j plus fi plus 1 j plus 1. These three terms are dedicated to this one, f of xi plus 1 y, for this integral. Fine. So in this way, total we will have 3, and again for each terms we will have 3 different terms. So total 9 terms are involved here for this double integral, and this is for only one subinterval part j minus 1 to j plus 1. Okay, so again you will be given some function fxy, so you can collect all such integrals from some initial point to the final point, and then adding all these integrals will lead to the final answer. Okay, let's try to understand this with one more problem. Apply Simpson's rule here to evaluate this integral 2 to 2.6 and 4 to 4.4. Now you can see here that a, b and c, d all are different, and your function fxy is 1 upon xy here. Okay, so what will be the solution here? Taking h is equal to 0.2 and k is equal to 0.3. Now see, this is wise decision, because here if you consider h is equal to 0.2, then you will have three parts here for 4 to 4.4, and for k if you consider 0.3, then you will have again two parts. So basically m and n is equal to 2, and what we are going to write here, so please keep in mind, this is basically my c2d and this is my a to b. Okay, you can even switch the functionalities as well. I mean, you can consider here a is equal to 2 and b is equal to 2.6. So in that case your h will be 0.3, and if you consider c is equal to 4 and d is equal to 4.4, then your k will be 0.2. Okay, so don't mind, you may consider the other way around. Now I is equal to hk by 9. So I is equal to hk by 9, again from this formula itself. This is the formula, and how do we proceed here? So hk by 9, now the first interval will be 4 4 4, fine, then 4.2 4.2 4.2, then 4.4 4.4 4.4. Okay, so basically 4 to 4.4 with step size 0.2. So we have considered this integral, and then 2, then 2.3 and 2.6. So in this way we have two steps process. So here I'm going to cover these 9 entries now. 4 2, then 4 2.3, and again this is middle entry, so 4 times this plus f4 2.6 plus 4 times this is my first integral, this is my last integral, and this is my middle. All the integrals, only a single integral lies here, so that is 4 times f 4.2 comma 2 plus 4 times f 4.2 comma 2.3. See here 4.2 is fixed in the middle entries, but here 2, then 2.3 increment of 0.3, and again 2.6. Here 4 is fixed, an increment of 0.3, so starting point is 2, then middle point is multiplied with 4, then again 0.3 increment here, so 2.6. In the same way you can go further. So now see here, this was it was 4, here 4.2, and now 4.4. Okay, so third entry will be 4.4. So f 4.4 comma 2 plus 4 times f 4.4 2.3 plus f 4.4 2.6. Okay, now you can find out these all entries because you know the function fxy is 1 upon xy. So we have found out these all values, substituted here, simplified it to get the desired answer. So in this case the answer is I is equal to 0.025. Fine. So in this way you can derive any kind of double integration formula. Just you have to employ the formula for the single integral, and then go on with adding all these layers. So basically you are working with any kind of rectangle, and you are just summing up all these integrals in a same pattern, the pattern which you have studied for single integral. I hope with this you might have a clear idea about the application of double integrals in the case of trapezoidal rule or Simpson's one-third rule. Thank you very much.